Okay, in this video, we're going to look at how you would solve this kind of problem. So hopefully you had a chance to try it on your own, and this will just walk you through what to do if you got stuck. So the first question here is, they tell us the average salary of a professional baseball player is increasing by about 12% per year since 1970. And they say in 1970, a player earned $29,303. They are asking us to use 1970 as our initial year zero. So the first thing they want us to do is create an exponential model. So in this case, I would say y equals ab to the x. That's my exponential model. And I know the initial amount is 29,303. And they are increasing by 12%. So I'm taking that 100% and I'm adding 12% to it each year. Okay, so in this case, I could reduce this one to 1.12 to the x. Okay, what is the average salary of a player today? Well, this is where this is important. Since 1970 is the initial year zero, and currently, as of this video, it's 2020, that means that 50 years has gone by. So when I go to use my model, I am going to substitute in 50 for my years. Okay, now that gives us about 8,468,631 and 17 cents. So they're saying in 2020, based on this model, we would a player would currently be making about $8.5 million. Okay, do I agree with this? Probably not, and I'll tell you why. When we go outside of our data range, then the model is not as accurate. So since 2050 is so far past our range of data, that might not be realistic. Okay, so let's take a look at some of the actual data that I'm talking about. So these are average baseball player salaries from 1970 to 2015. So when I use the model for the model from 1970 and I try to do it for 2020, that's kind of outside of this range for this. Okay, let's check out how to do this on using regression on Desmos. So we're going to take this actual data and go put it in Desmos and come up with a regression model. So if you notice, I did the y and then the little tilde, ab to the x, that tells the Desmos that it's going to do regression. And then I took my table and I typed in all the values. And I can see on here that it's telling me the A value is 198,477. And then my growth factor there is 1.07-ish. Okay, I can see how this model is matching the dots. It's definitely an exponential looking curve, and it fits loosely. It's not as nice and pretty as that one we did earlier. But let's check out the equation that we were using based off of 1970. So remember that equation was y equals 29,303, oops, parenthesis 1.12 and to the x power. And we can kind of compare the two. So you can see the purple line there is the equation just based off of the fact that we know what the initial amount is and what the percent of increase is, the average percent. The table value, the regression model, gives us based on some actual data. So I would say it looks like the regression one that we've calculated based on some real data there, that looks like it fits a little bit better. So our equation that I would write here is y equals, we had the 198,477 roughly, and 1.07, again, I'm rounding that off a little bit. You notice that they kind of line up fairly nicely, a little bit better than the other model. So our regression curve does fit some of the dots a little bit better. Some are a little low, some are a little high, but it looks like it's kind of going through them. Whereas our other model, the purple model, it doesn't look like it fits as well. Okay, so how well did they line up? I would say it lined up, it was okay. It was fairly well. The growth rate between the two, you can definitely tell is a little off. This was 7% and this was 12%, so a little bit off by about 5% there. I would say one of the big things for the discrepancies is that it was going from such a small amount to such a large amount, and this was over a long period of time, so then that model tends to get off a little bit more. Okay, so that hopefully explains some of this of how to do regression and how we're looking at exponential models as well and making some comparisons. So that is it for this video.